In section 3.3, we're going to look at the addition rule. We've already had one important definition earlier in the section, and that was the definition of two events being independent. Recall that we said that two events are independent if the occurrence of one event does not affect the probability of the occurrence of the second event. The new definition, which is going to be new to section 3.3, is that of two events being mutually exclusive. We say that two events, A and B, are mutually exclusive if they cannot occur at the same time. An example of a pair of events that would be mutually exclusive would be, suppose we roll a single-sided die, or a single die I should say, and let's let event A be that of rolling a 3, and event B of rolling a 6. On a single trial, we can either roll a 3 or a 6, but they can't happen at the same time. So these two events, A and B, would be mutually exclusive because they cannot happen at the same time. However, if we look at, let's say, two different events, event C is that of rolling an odd number, and event D is that of rolling a 5. If we roll a die, and if the number 5 shows up, then both event C has occurred because we rolled an odd number, and event D has occurred because we did indeed roll the 5. So because C and D can occur at the same time, this means that events C and D are not mutually exclusive. Okay. So again, pay close attention to the definition of mutually exclusive. It's actually worded in the negative. So to be mutually exclusive means that they cannot happen at the same time. And then if two events can occur at the same time, we simply label them and refer to them as being not mutually exclusive. Let's take a look at example 1. Suppose we have these three events. The event of a student being selected as a female, event B is that the student selected as a male, and event C is that the student selected as a criminal justice major. If we want to discuss whether or not events are mutually exclusive or non-mutually exclusive, it's a quality based upon a pair of events taken simultaneously. For example, if we look at A and B, a student being female and a student being male, those could not happen at the same time. You'd fall into one of the two classifications, just kind of blanketly, which means that those two would be mutually exclusive because they cannot occur at the same time. However, if we look at, let's compare, let's say A and C as a pair. Event A and event C would not be mutually exclusive because it's entirely possible to select a student female that also is a criminal justice major. So because A and C can happen at the same time, that means that they are not mutually exclusive. And for the same kind of reason, similarly, B and C would also not be mutually exclusive because it's possible to select a student that's a male criminal justice major, which would mean that both B and C would occur. So in terms of our pairs, A and B as a pair would be mutually exclusive, whereas A with C and B with C would not be mutually exclusive. Graphically, if we wanted to show a Venn diagram for what mutually exclusive sets would look like, because they cannot happen at the same time, there would be no intersection between the two sets. They would be entirely disjoint. Whereas if you have two events or two sets that are not mutually exclusive, then they would have some intersection that contains common elements. This brings us to a very important type of question within probability, and that is the probability that event A or B occurs. And for us, we'll be using what's called the inclusive sense of the word or, where for us, A or B would happen if either A occurs or if B occurs, or we allow for the possibility that maybe both A and B could happen at the same time. Okay. So again, buzzwords are key in this section. We've seen the word and apply to two events in sequence previously. We've seen conditional probability with the word given, and now we're looking for the probability of A or B. And this brings us to the addition rule. The addition rule says that the probability of A or B, this is equal to the probability of A plus the probability of B minus the probability of A and B. Okay. And what would happen here, the reason for the subtraction is, let's suppose that A and B are two events that have some common items that are part of them. Those individual items would be included both in the count for the probability of A and also in the probability of B, so there would be some overlap. So to avoid that overlap or that double counting, that's why we subtract by the probability of their intersection, which would include the events that are common to both sets. However, if it turns out this addition rule would actually simplify, in the event that A and B are mutually exclusive, then this probability would be 0 because they cannot occur at the same time. Let's take a look at example 2. Let's let event A be the probability of rolling less than a 3. On a die, the numbers that are less than 3 are 1 and 2, so this would have probability 2/6. Event B, the probability of rolling an even number, well, the even numbers are 2, 4, and 6. That would be 3 out of 6. And if we want to find the probability of rolling a less than a 3 or an even, it's the probability of less than 3, which is 2 out of 6, the probability of rolling an even, which is 3 out of 6, but then we need to subtract the probability of rolling a number that is both less than 3 and even. And if we think about which numbers are less than 3 and even, that's just going to include one outcome, which would be the outcome of rolling a 2. A number 2 is simultaneously less than 3 and is also an even number. And we know that the probability of rolling a 2 would be 1 out of 6. Therefore, the answer to this problem would be 2 out of 6 plus 3 out of 6 minus 1 out of 6, which is going to be 4/6 or 0.667. Let's take a look at example 3. Suppose we draw a single card from a deck of cards. Let's find the probability that we draw either a king or a heart. So let event A be that of drawing a king. Let's let event B be that of drawing a heart. According to the addition rule, the probability of a king or a heart would be the probability of a king. There's 4 kings in the deck out of 52, so that's 4 out of 52, plus the probability of drawing a heart. There's 13 hearts out of 52 cards, and then we have to subtract off the probability of getting a card that is both a king and a heart. Well, a king and a heart, that's just one card in the deck. That's specifically the King of Hearts card, and there's just one of them out of 52. So in this case, the probability of A or B is going to end up being 16 out of 52, which would be about 0.308. Let's look at another one. Suppose we draw a single card from a deck of cards. Let's find the probability of drawing a red suit or an ace. Again, we pick up on that buzzword or, so we know we're going to use the addition rule. This should be the probability of drawing a red plus the probability of drawing an ace minus the probability of drawing a red ace. Well, half the deck is red, so that's going to be 26 out of 52 for the probability of drawing a red card, plus the probability of drawing an ace. There's 4 aces out of 52, minus the probability of drawing a card that is simultaneously red and an ace. In the deck, there are 2 red aces, namely the ace of hearts and the ace of diamonds. So the probability of drawing a red ace would be 2 out of 52, and altogether we get that this total probability is going to be 28 out of 52, which should simplify to 0.538. Let's take a look at example 4. Suppose that at a student rally we have 20 Republicans, 13 Democrats, and 6 independents. We're going to select one student at random. Let's find the probability that the student selected is a Democrat or an independent. Again, it's an or probability, so we're going to use our addition rule. This would be the probability of a Democrat plus the probability of an independent minus the probability of someone who's a Democrat and an independent simultaneously. Well, there's 13 Democrats, and we would need to know how many individuals there are altogether. We had a total of 20 plus 13 plus 6, which lets us know that there was 39 individuals altogether. 13 of them are Democrats, so the probability of selecting a Democrat is 13 out of 39. There were 6 independents, so the probability of selecting an independent would be 6 out of 39. But the event of getting a Democrat and that of getting an independent, those two events are mutually exclusive. You could be one affiliation or the other, but you can't be both simultaneously. So because those two events are mutually exclusive, that could happen 0 out of 39 ways. In other words, that piece of it would have a probability of 0. So we get as our final answer, it's going to be 19 out of 39, which would be 0.487. The next example we're going to look at is coming from our stratified table. In example 5, we have a bunch of blood types for 409 individuals that are stratified in terms of the blood type, O, A, B, and AB, and also according to the different type of Rh factor, whether it was positive or negative blood. In part A, we're asked to find the probability that a donor had type O or type B blood. This is an OR probability, so again we would use the addition rule. This is going to be the probability of O plus the probability of B minus the probability of O and B. There's a total of 184 out of 409 type O plus the probability of B. There's 45 out of 409 for type B blood. And then the event of selecting someone with type O and selecting someone with type B, those two events are mutually exclusive. So the probability of the AND event would just simply be 0. They can't both happen at the same time. That can happen 0 ways out of 409. So we would get for our final answer, it's going to work out to be 229 out of 409, which is 0.560. In part B, when we want the probability of O or Rh positive, so again, keyword OR, the probability of O is 184 out of 409 plus the probability of positive Rh factor. That's going to be 344 out of 409. But then we would need to subtract those that are both O and Rh positive. O and Rh positive, that would speak to these 156 individuals. So the probability of O and Rh positive would be 156 out of 409 for a total probability of 372 out of 409, which would be 0.910. So look at part C. Let's find the probability that the donor has A or Rh negative. It's another OR probability, so we're using the addition rule. The probability of A is 164 out of 409. The probability of an Rh negative would be this row sum. That's going to be 65 out of 409. And then you have to subtract off those that are both A and Rh negative. Well, the A and Rh negative would be these 25 out of 409 individuals. So altogether, we would have a probability of 204 out of 409, which is just a shade under a half, 0.499. One of the important things to kind of keep in mind, especially in terms of definitions, is we don't want to confuse the dependent-independent events with those of being mutually exclusive and not mutually exclusive. Okay? For example, let's suppose we roll a 6-sided die and we flip a coin at the same time. If we define event A to be that of rolling a 6 and event B of that as getting a head on the coin, these two events would be independent events because, again, the occurrence of one isn't going to affect the probability of the occurrence of the other event. Nonetheless, these two events would not be mutually exclusive because it's entirely possible for them to happen at the same time. You could first roll a 6 on the die and then flip a coin and get a head. So because they could happen at the same time, that means that they are not mutually exclusive, yet nonetheless they're still going to be independent because the occurrence of one event isn't going to influence the probability of the occurrence of the other event. We'll finish with one more example. Let's take a look at question number 14. This is a conference problem. Suppose we have a math conference that has an attendance of 4,950 people. Of these, 2,110 of them are college professors, and 2,575 of them are female. Furthermore, of all of the college professors, 960 are female. The first question asks, are the events of selecting a female and selecting a college professor mutually exclusive? And the answer is going to be no. It's entirely possible to select a female college professor, of which we know that there are some at this conference. So because those two events can happen at the same time, that means that they are not mutually exclusive. Okay. Part B asks us to calculate the probability that if we select a person at random, that person is a female or a college professor. So this is another OR probability, so we're going to be using the addition rule. This would be the probability of selecting a female. Well, we know that there are 2,575 females out of our 4,950. Therefore, the probability of a female is 2,575 divided by 4,950 plus the probability of getting a college professor. We know that there's 2,110 college professors out of the 4,950 individuals. And then we would need to subtract by the probability of getting someone that is both a female and a college professor. Well, they tell us that there are 960 college professors that are female, so that's 960 out of 4,950, for a total probability of 3,725 out of 4,950, which would give us 0.753. I'll skip example 18, I'll let you try that one on your own. Let's do one last example of a stratified table. Suppose we look at a situation where in a sample of 1,000 people, 525 males, 475 females, we are told that 113 are left-handed, of which the 63 were men and 50 were women. So we have our table. Again, it's stratified according to both gender as well as handedness, whether left-handed or right-handed. The first question asks us to compute the probability that an individual selected is either left-handed or female. That should be the probability of left plus the probability of female minus the probability of a left-handed female. Probability of someone left-handed would be 113 out of 1,000. Probability of a female would be these 475 out of 1,000 minus the probability of a left-handed female. Well, the left-handed females would be these 50 out of 1,000. This will leave us with a probability of 0.538. If we look at right-handed or male, that's the probability of a right-handed person, that's 887 over 1,000, plus the probability of a male, that's 525 over 1,000, minus the probability of a right-handed and male. The right-handed males are 462 out of 1,000. This works out to be 950 over 1,000, or 0.950. If they say the person is not right-handed or is male, that's just kind of another way to say left-handed or male, right? So if they're not right-handed, then by default they're going to be left-handed. The probability of a left-handed person is 113 over 1,000, plus the probability of a male would be 525 over 1,000, minus the probability of somebody that is left-handed and male. Well, left-handed and male, that's going to be these 63 out of 1,000 for a total probability of 0.575. For part D, notice that the change in verbiage here, they changed the word, we're looking for an and probability. Part D says, what is the probability that someone is right-handed and female? We can look that up directly from the table. The number of right-handed females is simply going to be 425 over 1,000 for a probability of 0.425. And the last question we have in this section is, are the events of being right-handed and being female mutually exclusive? Well, the answer is no. We have, in particular, there are individuals that are both right-handed and female. So because it's possible to be both right-handed and female, those events can occur at the same time, which means that they are not mutually exclusive.